Hi, in this video we are going to show how we can formulate the optimal control design problem for discrete time systems as an optimization over sequences, over control sequences. Let me remind you that this video is given within a course on optimal and robust control given at Czech Technical University in Prague. The setup for us is this. We would like to minimize the cost function, which will be composed of the term penalizing the state at the final time and possibly the final time itself, and then the combined term corresponding to the state and the control throughout the interval of control or horizon of control. We will label the cost functions as J in this course, and note that they are functions of both the state and the control. Therefore, the optimization variables here are really sequences of controls and sequences of states. Now the constraints here, the first constraint that is always here is in fact the state equation describing the dynamics of the system, and then potentially the initial state could be specified, typically it is, and possibly also the final state could be specified, in which case it does not make sense to include it in the cost function. Then moreover we can have some constraints on the control signal and the state variable themselves. Formally we can include these constraints on the initial and final state into some general equality type constraint G, and similarly the inequality type constraints we will label as H. Now since here, let me remind you that the cost function is a function of both x and u, which are coupled through the state equation. Therefore we call this approach as a simultaneous framework. What we could however do is now we can use the state equation to actually eliminate the state variables from the cost function, and this will give us a new cost function. Let's label it J tilde, which will only be a function of u and possibly x0, or in fact it should be xi to keep the notation. And this this approach is called sequential approach, and I will illustrate it in a while by means of an example. In particular, we will consider linear system, we will consider quadratic cost, and we will consider the so-called regulation task, in which the goal is to bring the state to zero. Now, the cost function will look like this. It will be 1/2 of the term corresponding to the state at the final time, and 1/2 of the sum of the terms corresponding to states and controls throughout the interval of control. And now the interval of control starts at 0 and goes to n, but note that u is only considered at n-1 interval, because that's the only time when it influences the state at n. Now the constraints come in the form of a classical state equation, and the initial state is given. First, we will not consider constraints here. Now, what we will do in the following is that we will take all these state vectors and stack them into one long, super long column, similarly with the control signal. So then we can write down the cost function in the following way. Explicit way. So the cost function, so the term corresponding to the state at the final time will have this long x vector transposed. In fact, I forgot to include the transposition signs with each individual axis. And then here the weighting matrix will be block diagonal with the last element corresponding to the penalty for the final state, and similarly for the controls. Here also the weighting matrix will be diagonal or block diagonal, containing our matrices on the diagonal. And finally, I will explicitly here separately state the term corresponding to the initial state. Its role is certainly different from the roles of states at other time instances, in that it's fixed. Now the constraints. Here it may take just a few moments for you to recognize that this is indeed how the state equation could be written down. So here I will have some matrix not yet specified times the long stacked vector x plus another matrix times long stacked vector of controls plus yet another matrix times the state at the initial time. Now how about the matrix that relates the states? It's in fact, it looks like this, then yeah, so check it out by yourself. And I will label these matrices as Q bar, R bar, this will be A bar, and this will be B bar, and possibly this A naught. Now this in fact could be regarded as a quadratic problem already, but if you like, we can now combine the states and the controls into just one long vector, and then we will formulate the optimization as really minimization of this pure quadratic form. How about the constraints here? Yeah, I will in fact disregard the term corresponding to the initial state here because it's just a constant offset. And how about the constraints here? In order to see how they look like, let's now write down explicitly here that the long vector x can be expressed like this. This is what we had up there. Now moving everything on the left hand side, this is what I get. And finally stacking together x and u in one combined vector w, this is what I get. So clearly this is a linear constraint, or constraint in the form of a set of linear equations. Perhaps we can label this as a double tilde times w is equal or plus b tilde is equal to 0. So clearly linear constraints, and this renders our problem perfectly suitable for solving by quadproc function. Now I've mentioned up there that we can also eliminate the state variables altogether, so let's do it now. Either we can write now the long x vector as a function of the long u vector and the initial state, or if you want, and I can do it in this matrix vector form, or we can do it in a step-by-step way. So first I write x1, then x2, and obviously x2 depends on x1, which I can express from the equation above. I think this procedure is pretty much familiar to you. Obviously what I will do now is I will express x at some general time k, and this is already pretty obvious where we are heading. So if I now proceed by stacking all these state vectors into that one long vector, this is how the relationship between this long x and long u, how it looks like. You can again check by yourself. Now you can perhaps recognize here really pretty much familiar pattern. Doesn't it look like, I mean, this block lower triangular matrix, doesn't it looks like a controllability matrix? Let's label this as C bar and the other matrix as, say, A hat. And now from this I can substitute into our cost function as we derived above in this format using these long vectors. This will obviously be a new cost function, so here I'll substitute for the state vector at the final time this, Actually, sorry, no, not at the final time, but the whole vector. And similarly, the term corresponding to controls, and finally the term corresponding to the initial time. Now this now becomes somewhat technical, but let's go through it in order to get some final results. So I will multiply out the brackets and combine all the terms that could be combined. So let's give it a few more moments. Alright, so now what I can do is now I can combine the terms that are related, so all the quadratic terms in u and quadratic terms in x0 or x0. So let's do it now. Now this is the term that is linear in u, and finally the term that is quadratic in the initial state. Now, since the initial state we assume as fixed, as given, this only brings some constant offset, and therefore we can disregard it from the optimization. So now this will be somewhat an abuse of a notation to write that this is the same cost function. It's not, but from the optimization perspective it's identical, or it doesn't make sense to distinguish. So now I will label the two new matrices as capital H and capital F transposed. Therefore my cost function looks like this. And this is our old friend, quadratic function, right? So finding its minimum is as easy as finding the gradient with respect to the optimization variable, which is u. It's this linear function, and we are setting the gradient to 0, which brings us to the standard set of linear equations which we will solve in this way. In MATLAB in particular, forget about using the inv function, the function for computing the inverse. In fact, instead we will use the backslash command for sure. Now this was for a situation without constraints, but if there are constraints on the control signal, remember that the control signal or sequence is the variable here, so it's as easy as imposing some additional or imposing some constraints on the optimization variable, for instance lower bound, upper bound and lower bound. These can be in fact reformulated again in the matrix vector form in this way. So here I will again have the stacked vector, control vector, and then the coefficient matrices will look like this. Again, this is a piece of cake to verify. So clearly this way what we get is quadratic optimization with linear constraints. We may also want to add constraints on the states or possibly even the outputs. But how can we now do this here in the after the elimination where x no longer exists in our problem? Well, here we will either go back to the simultaneous framework where the state variable appears explicitly as a variable, or we can invoke the matrix that we derived up there, the matrix that we labeled as C bar, the matrix with which we can transform our control vector into the state vector. Again, we also have to, we can't forget the influence of the initial state. So with this now, the requirement that, for instance, x should be upper bounded by x max, this could be again rewritten in the format of these long vectors like this. where x max will be again the long vector. Well, you may perhaps add a few more embellishments here, but I will stop here. Instead, I will like to emphasize what is the outcome here. The outcome here is the sequence of control signals, which means that we have an open loop control strategy. However, we know fairly well that most often than not we need feedback. But how do we use this scheme in feedback? The answer is receding horizon, also known as model predictive control, which will be the topic of our next video.